Hi guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at the complete ideal batch reactor design, analysis and problem solving. So just to give you a quick overview as to what we're going to look at in this particular tutorial is we're going to cover the following key elements. We're going to look at the general nomenclature associated with reactor and reaction design. We'll look at the full derivation of the material and the energy balances for a batch reactor. We'll then look at extensive analysis of the rate constant and its importance within reactor design and reaction engineering. And then we'll finalise off with a full working solution from a real problem. So if we dive straight in and have a look at some of the nomenclature just for you to remember going forward. The first term is isothermal. So an isothermal simply means we have a constant operating temperature. An adiabatic system means that we have no heat or mass transfer to or from the surrounding system. And that would then mean that a non-isothermal would have a varying mixing temperature. A non-adiabatic would have heat or mass transfer, or both, to or from the surroundings. Now, one other key term is steady state. Steady state simply means that whatever enters the system must leave the system, i.e. we have no accumulation taking place within the vessel. Now, if we take a look at the assumptions that we need to make when we design an ideal batch reactor, then the assumptions will allow us to simplify the equations and make the mathematics a bit easier in order to solve the problem. Now, the assumptions are for an ideal batch reactor is that we have no in or out flow, so therefore the steady state argument doesn't apply in this case. We will have perfect mixing, we'll have a uniform temperature distribution, and we'll have a uniform concentration throughout the entire vessel. Now, the more assumptions that you make, the easier the design will be, but the further it will deviate from a real reactor system. And that is the problem that is associated with these assumptions, is that if you want to design real reactors, then the idea of uniform temperature distribution, perfect mixing, doesn't actually apply. So in our extensive reactor design course, what we basically do is we uncover things called a bypass and a dead zone that you have to account for if you want to design real industrial reactors, because this will have an adverse effect on the batch time, the conversion with respect to time, the residence time within the reactor for continuous systems, and so forth. So that's what you would need if you wanted to design industrial scale reactors. Now let's take a look at the material balance first, and then we'll look at the energy balance. So when we model any reactor, we have to apply the general mole balance. And the general mole balance is simply basically saying that the amount of component A, so we use a reference component, the amount of component A that's introduced per unit time must be equal to the amount that leaves, plus or minus, depending on where your reference component lies, if it's a reactant or if it's a product, is plus or minus the amount of A that reacts per unit time and the amount that is accumulated per unit time. Now, if we wanted to express this as mathematical nomenclature, then what we could do is express it looking at something like this, where we have F naught Ca naught. So the naught indicates the inlet and the F is the flow rates. Ca naught is the initial concentration, Ca is the final concentration. We have the reaction rate multiplied by the volume of the vessel, and then the volume of the vessel multiplied by, now this is a partial differential between the concentration and time, and we'll deal with that in just a second. Now, the assumptions that we made, however, we can actually simplify this system a bit further, because we have no in or out flow to the system. So therefore, the first two terms can actually be removed. And that leaves us with the amount that reacts per unit time and the amount of accumulated per unit time of component A. So what we can then do is cancel out the volumes, because in batch systems, the volume is fixed. So therefore, it doesn't really play a part in the overall model. Different with continuous systems, whereby the volume of the material can fluctuate over time if we have accumulation taking place. Now, if we rearrange this and bring the accumulation term across to the other side, and we then say that because of the assumptions that we made, we change this from a partial differential to a full differential equation. Now, ultimately what we want here is, with batch systems, is we want to work out the time it will take for the reaction to either go to completion or to reach a certain conversion. So what we have to do here is rearrange this system for time, and that's our dt. So we create a differential equation, which then, if we integrate both the left and right hand side, then the integral of dt simply becomes t. And that's just using the basics of integration. Now here, what we need to do is we need to integrate this with respect to the concentrations. So our upper concentration will be Ca, because that's going to be the final concentration, and Ca naught is going to be our initial concentration at time 0. Now, arguably, you're going to say, well, the Ca naught will surely be higher than the Ca, and that is indeed correct, and that's why we have the minus here. So if we invert the limits, we get rid of the negative sign. So therefore, our integral becomes the integral of Ca naught Ca dCa by minus Ra. Now, it's more often than not better to express the batch time in terms of conversion rather than in terms of, concentration. So what we can do here is use this relationship, which links any final concentration to the initial concentration as a function of conversion. Now, in order to create this relationship, you can perform a species table on a very generic system, and you will be able to prove this relationship. Now, what we can then do is simply apply the same methodology, but turn this into a differential equation. So if we differentiate this with respect to x and time, and we put this back into the equation, we can represent this for minus Ra. So our equation that we're going to use going forward for the batch time of the reactor is going to be T is equal to Ca naught, which is independent of the integral, because that's fixed, that's not going to change. So we can remove this from the integral, and then we have between 0 and our final concentration of x, dx over minus Ra. So that's the relationship that we're going to use for our material balance in order to determine the batch time with respect to conversion. Now, building on from this, we can then apply the same methodology but to the energy balance. Now, one of the assumptions is this is for an isothermal derivation, and if you remember from the definitions for what isothermal means, then that will help us deduce the simplifications of the energy balance. So the general energy balance is given by the accumulation is equal to the amount of energy comes into the system minus the energy that leaves the system, plus or minus the energy transfer, plus or minus the heat of the reaction, and plus or minus the work. Now, the energy in comes in the form of enthalpy. And since we have no in or out flow, we can also assume that the work here is negligible. We have adiabatic conditions, isothermal conditions, we can simplify this entire equation to the accumulation must be equal to the heat of the reaction, which, because this is heavily assumed, it's an ideal batch reactor, then a lot of these simplifications will have an influence on the overall design if you wanted to design a real system. But you can see the power of heavy amounts of assumptions. We've managed to reduce this entire equation down to two terms. Now, as I mentioned before, the energy is in the form of enthalpy. So the accumulation is going to be the amount of enthalpy with respect to time. Because remember, in the batch system, this is the batch time. Now, the heat of the reaction is going to be the heat of the reaction for that particular reaction multiplied by the reaction rate multiplied by the volume of the system. Now, if we rewrite this in its raw state as a function of temperature, then the enthalpy is mCp delta T. Now, what we can then say is that we can vary the temperature, so dt capital T denotes temperature, lowercase t denotes time. Then we could have mCp delta T over dt is equal to the heat of the reaction. Now, from here, we can replace the reaction rate as a function of conversion, which we've seen in the material balance. So therefore, we can now start to simplify this system even further, because what we can then say is that the mCp delta T is equal to the density multiplied by the volume multiplied by the specific heat capacity. And you'll then start to see the simplifications that take place, because we now have this relationship again with volume. And what we can also do here is, instead of expressing delta T, i.e. the change in the temperature, we can express this as the final temperature minus the initial temperature. We can then cancel out the volumes on both sides, and if we rearrange for the final temperature, then what we end up with here is this equation. And this is the final temperature as a function of conversion. And that's really, really powerful in terms of working out the energy side of this particular system. And this is the equation that we're going to use moving forward. Now, before we consider the non-adiabatic system, because it's a good idea to look at the adiabatic and then the non-adiabatic, just so that you have a complete overview that, depending on the problem that you're trying to solve, you have both the energy balance equations to hand. But before we do that, let's just quickly summarize the material and energy balances we've looked at so far. So the material balance that we've derived from the previous set of equations is that we have the initial concentration multiplied by the change in the conversion must be equal to the batch time multiplied by the reaction rate constant, and then we have our energy balance here as well. Now, we can also express these in the following way. I personally don't like expressing it in this form, so instead of having the delta x and the delta t, you actually show each individual component. So you show xn plus 1 and xn. Same thing with the t's. I personally don't like it because you are adding more variables and the equation can become quite messy. But again, it's entirely up to you and how you would actually go about solving your particular system. Now, for the adiabatic system, we include the transfer term in the balance, and that's where this Q comes into play. So that's just to give you the heads up as to where this Q has come from. So the non-adiabatic wouldn't have this Q here. So that's just giving you the heads up. So for non-adiabatic systems, then that remember that means we have energy transfer either to or from the surroundings. So what we need to do here is rearrange for our delta T, which is for time, and our delta T for temperature. So if we rearrange for the time parameter using the material balance, then what we end up with is this particular system here. So we have Ca naught delta X over minus Ra. We then incorporate our energy balance. Now here, the Q is the energy transfer to or from the surroundings. And that would either be plus or minus, depending on how we define our system. So therefore, for our change in temperature as a non-adiabatic system, we end up with this correlation here. So you can see it's slightly more involved, but with the inclusion of the Q term. And again, you could break that Q down, because Q is UA delta T. That's the overall, if you account for the overall heat transfer coefficient, but you have multiple equations for Q depending on the information that is available to you. So this has dealt with the material and the energy balances, and before we look at a full problem, it's worth considering the rate expression, because a lot of the time the tutorials and the resources that are available tend to overlook the rate expression within the same tutorial. They tend to look at it at a slightly different time. So it's a good idea just to bring everything together so as that you can use this as a full comprehensive guide. So we've defined minus RA and spoke about it in the context of the reaction rate. But what does it actually mean? And it depends if we talk about the reactants or the products. The definition will change ever so slightly. But typically what we tend to do here is refer to the reaction rate as the consumption of the reactants. So usually component A is one of the reactants. So what we can then say is we can define what minus RA is. And minus RA is going to be the rate constant for this particular system multiplied by the reactant concentration. So that means that whatever the rate constant is, multiplied by the reactant concentration over an extended period of time, will tell you what the overall reaction rate is going to be. Now, why does this matter in terms of reactor design? Well, when we talk about reactor design and we look at reaction engineering, the reaction rate, the K value, is highly dependent on the order of the system, because the units are going to change significantly. Now, how do you work out the order? Well, the order is dependent on the stoichiometry of your reaction. But when we model these, two key assumptions have to be made in order for us to make this connection between the stoichiometry and the order. So the two things that we have to assume is that we have an elemental reaction and power law kinetics apply. These are how we can use the stoichiometric coefficients to determine the overall order of the system. Now, if you want to know more about what these assumptions actually are individually, so what an elemental reaction is, what power law kinetics actually is, then let me know in the comment section. And we can always look at creating a tutorial, but we already have that material in place in our fully comprehensive reactor design course. I'll put a link in the description to that if that's something that you're interested in going from the most basic to the most advanced reactor design methodologies. But let's take this a step further and let's consider the reaction rate as the concentration and temperature system. So we've looked at it from the kinetics point of view, but if you look at it from the concentration and the temperature, then we have to bring in the Arrhenius equation. Now, I already have tutorials available for the Arrhenius equation. I'll put a link in the description to that particular tutorial, which goes into the detail of the Arrhenius equation. But ultimately, the Arrhenius equation expresses the relationship between the reaction rate, so K, as a function of temperature. Now, if the reaction can be expressed as a linear function, i.e. what we have above, then the power law kinetics can apply, so therefore we can express minus RA in the following ways, whereby the alpha and the beta are the stoichiometric coefficients. So in this case, the value of alpha would be 2 and the value of beta would be 1. The value of Charlie, if you were to use this as an example, would be 3. So therefore the overall order of the system would be 3 plus 1 plus 2, so this would be a 6th order system, overall reaction. But the reaction rate with respect to A is 2nd order, with B is 1st order, C is 3rd order. Now, before we look at the example, this is the last part for the rate constant, is that dependent on the order will determine what the overall units of the system is going to be. So let's take a look at just a 1st and a 2nd order system. So if we have A goes to B, then this is a 1st order system. So i.e. we have K, and that's Ca to the power 1. So that just remains as Ca. Therefore, if we rearrange for K, we end up with minus Ra over Ca. Now, therefore, we can substitute in each of those equivalent units. So the reaction rate is the kilomoles per meter cubed second, and Ca is kilomoles per meter cubed. Now, if you were to divide these, we get a reaction rate constant of 1 over S, so it's 1 over seconds. That's for a 1st order system. Now, say for example we have a 2nd order system, then we now have Ca to the power 2, which therefore means our denominator has to be squared. Now you can clearly see the impact and the difference that the order has on the reaction rate constant units. We've went from 1 over S to meters cubed per kilomole seconds for a 2nd order system. And you can apply the same thing for 3rd order, for 4th order, and so forth. Now, let's put this all together and we'll look at how to solve a working example. And we're going to do this in as much detail as possible so as that you can see how we apply everything that we spoke about in this tutorial. So we have a gaseous reaction which is given by 2A goes to B plus Z. It's carried out in a batch reactor with constant volume, which makes sense, and the reactor operates at 600 Kelvin, 2 atmospheres, and we need to determine the conversion at 0.1, 1 and 10-minute intervals. We then want to plot on a Cartesian set of coordinates, and what we have to do is you must show the batch time derivation as a function of conversion before solving. At these operating conditions, we are provided the rate constant at 0.8 meters cubed per kilogram mole second. So ultimately what we're going to do here is create a plot of conversion versus time. And the question is asking you for the derivation as a function of conversion. So what I would advise you to do is pause the video and see if you can solve this by yourself. And ask your question, how would you approach this particular problem? So the first thing that you would need to do in any problem with reactors and reaction engineering is list your set of assumptions. Because if you don't give us your assumptions, we can't follow your process or your methodology. We need to know what assumptions you're going to make so that we can ensure that the process is concurrent. So we have elemental reaction, power law kinetics, 2nd order reaction with respect to A. We've got all that. We now know that our rate equation becomes kCa squared, which makes sense. Now, if we start with the general batch time equation, then we have dCa over minus Ra, and this is it in its raw state. We haven't, flipped the units, so that's why the negative here still stands, but we can deal with that in a second. But before we go into the substitution, we want to express as a function of the conversion, because right now this is a function of concentration. So using the trick that we did before, what we can do is we can substitute in our minus Ra because we know what that is as a function of concentration. And what we can then do is take the rate constant out, because that isn't going to change as the concentration changes. That is a fixed value. That's not going to change. So we can take that out of the integral. If we apply the rules of integration, then we can rearrange, and we get kt is equal to 1 over Ca minus 1 over Ca naught. And then the question becomes, how do we express this as a function of conversion? Because right now, this is solved as a function of concentration, where we use the expression of Ca equals Ca naught 1 minus x. And this is a lot of my students that I teach here in Scotland, I usually call this the Callum equation, because this is one that I really say is the fundamental key to solving reactor design questions. It's the way in which you link concentrations and conversions to each other. So it's so powerful in being able to switch your equations from one variable to the other very quickly. So what we can do in this instance is we can substitute in our values and begin to simplify our system, because what we have here is a common factor of Ca naught. So we can bring these systems together, and using the simple laws of fractions, we can bring it so that it's x over Ca naught 1 minus x. We can then start to rearrange and bring our x terms to the left and correlate the rest to the right. So now we have our expression. We've derived our expression for conversion as a function of time. Because now what we need to do first is determine our initial concentration. We don't know that. Sometimes we're provided that in the question, other times we aren't. We were provided other pieces of information. So what we need to do here is, because we have a gaseous system, we can use the ideal gas law. And the ideal gas law for our initial concentration will be our molar volume, our operating pressures, and our operating temperatures based on ideality. So ideality meaning 1 atmosphere and 0 degrees Celsius or 273.15 degrees Kelvin. So in doing so, what we end up with is 0.04 kilimoles per meter cubed. So that's our concentration. That's our initial concentration of the system. Now we have everything that we need. We have K, we have Ca naught, and we will vary our temperature, our times, and then we can create our plot. So what I would tend to do is I would create a table that characterizes each increment that we want. Now what you have to be careful of is ensure that your time is in the correct units. We were provided the times in minutes. We need to convert these to seconds, because remember the units of K is per seconds. So by converting our times to seconds, substitute into the function, we get our respective conversions. Now what we expect is that the more time, so the higher the time, the higher the conversion. And that's what we're seeing. So at 6 seconds, we've only converted 16%. But at 600 seconds, we've converted 95%. So if you use, any software, here we used Microsoft Excel to create the following time versus concentration chart, then this is your plot on a set of Cartesian coordinates. So you can see here we have a very rapid reaction, and then it tends to steady itself off after, maybe approximately 60 seconds or so. So a very rapid reaction taking place. But that is the full solution for the derivation, for the applications of the ideal batch reactor design modeling, and a plot for batch time as time and concentration. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in understanding the concept and the idea of ideal batch reactor designs, the nomenclature, what the rate equation is, and how you actually apply these particular systems. Thanks for watching. Please like and subscribe to the channel. It really helps us reach as many chemical engineering students as possible. Thank you for your time, and we look forward to seeing you in another video.